Welcome to this comprehensive presentation on AWS Elastic Kubernetes Service DNS integration. As network engineers preparing for the AWS Network Specialty Certification, you will gain deep insights into how Kubernetes DNS works within AWS. This presentation will cover everything from basic DNS concepts in Kubernetes to advanced EKS-specific DNS configurations. We will explore how DNS resolution works, external DNS integration, and troubleshooting techniques. By the end, you will understand how to configure, manage, and troubleshoot DNS in EKS clusters. This is a critical skill for the certification exam. As network engineers, you are familiar with traditional DNS where applications query DNS servers directly. However, in containerized environments like Kubernetes, DNS works differently. In traditional environments, applications use the host's DNS resolver. But in Kubernetes, each pod gets its own DNS configuration that is managed by the cluster's DNS service. Think of it this way: instead of your application directly asking Route 53 for DNS resolution, it first asks the Kubernetes DNS service, which can then forward requests externally or resolve internal cluster services. This dual-layer approach provides service discovery within the cluster while maintaining external connectivity. EKS uses CoreDNS as its DNS server, replacing the older CubeDNS. CoreDNS runs as a deployment in the kube system namespace and handles all DNS queries within your cluster. The architecture shows how CoreDNS integrates with AWS VPC DNS. When a pod makes a DNS query, it goes through several layers: the pod's local resolver, CoreDNS, and potentially AWS Route 53. Notice how CoreDNS sits between your workloads and the VPC DNS resolver. This positioning allows it to handle both internal Kubernetes service discovery and external DNS resolution. The EKS worker nodes inherit the VPC's DNS settings, which CoreDNS then uses for external queries. This seamless integration is what makes EKS DNS so powerful. Let's start by creating an EKS cluster using native Amazon Web Services CLI commands. First, we will create the cluster control plane using the AWS EKS create cluster command. This is the Amazon Web Services command line interface for managing EKS clusters. The cluster name parameter specifies a unique identifier for your cluster. The version parameter 1.28 specifies the Kubernetes version. The role ARN parameter provides the service role that Amazon EKS will use to create AWS resources. The resources VPC config subnet IDs parameter specifies the VPC subnets where your cluster will run. These should include both public and private subnets across multiple availability zones for high availability. After creating the cluster control plane, we will create a managed node group using AWS EKS create node group. This creates the EC2 instances that will run your Kubernetes workloads. Cluster creation typically takes 15 to 20 minutes, as Amazon Web Services provisions all the infrastructure components. Once your cluster is ready, let us examine the DNS configuration. We will use the kubectl get pods command to list all system pods. kubectl is the Kubernetes command line tool that lets you run commands against Kubernetes clusters. The namespace flag kube system shows all system pods, including CoreDNS. You will typically see 2 CoreDNS pods running for high availability. The kubectl describe config map CoreDNS command reveals the CoreDNS configuration. This config map contains the core file, which is the CoreDNS configuration file. The core file defines how DNS queries are handled. The cluster local zone handles internal Kubernetes DNS, while the forward plugin sends external queries to the VPC DNS resolver. Understanding this configuration is crucial for troubleshooting DNS issues in your EKS cluster. This diagram illustrates how DNS queries flow within an EKS cluster. When a pod wants to communicate with another service, it triggers a DNS lookup. The query starts at the pod level, goes through the node's DNS configuration, reaches CoreDNS, and potentially forwards to external DNS servers. For internal services like webservice.default.svc.cluster.local, CoreDNS resolves these directly using its knowledge of Kubernetes services and endpoints. For external domains like google.com, CoreDNS forwards the query to the VPC DNS resolver, which then queries public DNS servers. This flow ensures that internal service discovery is fast and reliable while maintaining connectivity to external resources. Let's create a practical example. The kubectl create deployment nginx command creates an nginx deployment with 3 replicas for testing. The kubectl expose deployment nginx command creates a Kubernetes service that provides a stable DNS name and IP address for our nginx pods. The port parameter, set to 80, specifies the service port, while the target port parameter, also 80, defines the container port. The type parameter cluster IP creates an internal-only service. The kubectl run test pod command creates a temporary pod for testing DNS resolution. The remove, interactive, and TTY flags make it interactive and auto-delete upon exit. The nslookup nginx command from inside the test pod should resolve to the service's cluster IP, demonstrating internal DNS functionality. Understanding Kubernetes DNS naming is crucial for the AWS Network Specialty exam. Every service gets a predictable DNS name following specific patterns. The basic format is service_name.namespace.svc.cluster.local. For example, a service named web in the production namespace becomes web.production.svc.cluster.local. You can also use shortened forms. Web.production works from any namespace, while just web works only from within the same namespace. Pods also get DNS names, but they are based on IP addresses using the format pod ip.namespace.pod.cluster.local. However, this is rarely used in practice, since pods are ephemeral. These naming conventions ensure predictable service discovery across your entire cluster. ExternalDNS is a powerful Kubernetes controller that automatically creates DNS records in Route 53 based on your Kubernetes services and ingresses. The installation process shown here deploys ExternalDNS with proper role-based access control permissions. The service account needs specific permissions to read Kubernetes resources and update Route 53 records. The domain filter parameter restricts ExternalDNS to only manage records for your specific domain, preventing accidental modifications to other domains. The AWS zone type equals public parameter tells ExternalDNS to only work with public hosted zones. You could also use private for internal DNS records. Once deployed, ExternalDNS watches for services and ingresses with specific annotations and automatically creates corresponding Route 53 records. ExternalDNS architecture and flow. This diagram shows how ExternalDNS integrates with AWS Route 53. ExternalDNS runs as a pod within your EKS cluster and continuously monitors Kubernetes resources. When you create a service with the ExternalDNS hostname annotation, ExternalDNS detects this and creates a corresponding Route 53 record. The flow is as follows. First, you create a Kubernetes service. ExternalDNS detects the annotation. It calls the Route 53 API to create a DNS record. Then external users can now access your service via the custom domain. This automation eliminates manual DNS management and ensures your external DNS records stay synchronized with your Kubernetes services. For network engineers, this pattern is especially important for understanding how Kubernetes integrates with traditional AWS networking services. Here is a practical example of creating a load balancer service that ExternalDNS will manage. The kubectl apply command with the file flag creates the service from a YAML definition file. The annotation external-dns.alpha.kubernetes.io/hostname with the value app.example.com tells ExternalDNS to create a Route 53 record pointing to this service. The type load balancer creates an AWS ELB that provides external access to your service. EKS automatically provisions this ALB or NLB after applying this configuration. You can verify the Route 53 record with the AWS CLI command aus Route 53 list resource record sets. You should see an A record for app.example.com pointing to your load balancer. The kubectl get service nginx external command shows the external IP or hostname assigned by AWS, confirming successful load balancer provisioning. Sometimes you need to customize CoreDNS behavior. The configuration shown here demonstrates common modifications you might make for enterprise environments. The log plugin enables query logging, helpful for debugging DNS issues. The errors plugin logs error conditions. The rewrite plugin can modify DNS queries before processing. In this example, it redirects all example.com queries to internal.example.com. The forward configuration can be customized to use specific DNS servers instead of the default VPC resolver. This is useful for hybrid cloud scenarios. After modifying the CoreDNS config map, you need to restart the CoreDNS pods with -l rollout restart deployment /CoreDNS to apply changes. When DNS issues occur in EKS, follow this systematic troubleshooting approach. Start by checking if CoreDNS pods are running and healthy. The -l get pods command with the namespace flag cube system should show CoreDNS pods in running status. If they are not, investigate pod logs and events. Test DNS resolution from within a pod using NSLookup or DIG. These are standard DNS lookup utilities. This helps isolate whether the issue is with CoreDNS or external connectivity. Check the CoreDNS logs using the -l logs command for the CoreDNS deployment in the kube system namespace. Look for errors or unusual query patterns. Verify that the CoreDNS service exists and has proper endpoints. The -l get service command in the kube system namespace should show the CubeDNS service. Finally, check if pods have the correct DNS configuration in the resolve.conf file by examining a running pod. This table summarizes the most common DNS issues you will encounter in EKS environments and their solutions. DNS lookup failures for external domains often indicate CoreDNS cannot reach upstream DNS servers. Check security groups and network access control lists to ensure outbound DNS traffic on port 53 is allowed. Internal service resolution failures usually point to CoreDNS configuration issues or networking problems between pods, and CoreDNS slow DNS resolution might indicate CoreDNS resource constraints or upstream DNS server issues. Consider scaling CoreDNS or tuning its configuration. External DNS not creating records typically involves IAM permission issues or incorrect annotations on services. Understanding these common patterns will help you quickly diagnose and resolve DNS issues in production environments. Let's review essential best practices for DNS in EKS environments. These practices will help you design resilient, scalable DNS architectures. First, always run multiple CoreDNS replicas for high availability. The default configuration usually includes 2 replicas, but consider more for large clusters. Configure resource limits and requests for CoreDNS to ensure stable performance. DNS is critical infrastructure that needs guaranteed resources. Use DNS policies appropriately. The cluster-first policy is default and correct for most use cases, but understand when to use cluster-first with hostnet or default. Monitor DNS performance and error rates. Set up CloudWatch dashboards to track DNS query latency and failure rates. For external DNS, always use least privilege identity and access management policies and restrict domain filters to prevent unauthorized DNS modifications. Network policies can significantly impact DNS functionality in EKS. This diagram shows how to properly configure network policies to allow DNS traffic. The key is ensuring that all pods can reach CoreDNS on port 53 for both UDP and TCP. Network policies that are too restrictive can break DNS resolution. When implementing network policies, always include rules that allow egress to the CoreDNS service. The service typically uses the label selector K8's app CubeDNS. Also ensure that CoreDNS can communicate with upstream DNS servers. This usually means allowing egress on port 53 to the VPC DNS resolver. Test DNS functionality thoroughly after implementing network policies. A simple NSLookup from affected pods can quickly reveal DNS connectivity issues. EKS clusters can integrate with Route 53 resolver for advanced DNS capabilities. This is particularly useful for hybrid cloud scenarios where you need to resolve private DNS zones. Route 53 resolver endpoints allow your EKS cluster to query private hosted zones or forward queries to on-premises DNS servers. The inbound endpoint receives queries from your EKS cluster, while the outbound endpoint forwards queries to specified targets. To configure this integration, you create resolver endpoints in your VPC and then modify the CoreDNS configuration to use these endpoints for specific domains. This setup is common in enterprise environments where EKS workloads need to resolve internal corporate DNS names or access resources in other VPCs. Effective DNS monitoring is crucial for maintaining cluster health. This slide shows the key metrics and tools for DNS observability in EKS CoreDNS exposes Prometheus metrics that provide detailed insights into DNS query patterns, latency, and error rates. Key metrics to monitor include DNS query rate, response time, cache hit ratio, and error codes. High error rates or latency can indicate underlying issues. Use CloudWatch Container Insights to collect and visualize these metrics. Set up alarms for critical thresholds like DNS query failure rates above 5%. The kubectl toppods command can help identify if CoreDNS is consuming excessive resources, which might impact performance. This command shows CPU and memory usage for running pods. Consider using distributed tracing tools to understand how DNS resolution affects your application's overall performance. As you prepare for the Amazon Web Services Network Specialty Certification, focus on these key DNS concepts and scenarios. Understand the difference between cluster internal DNS, handled by CoreDNS, and external DNS, handled by Route 53 or other providers. Know how to troubleshoot DNS issues systematically. Check CoreDNS health, verify network connectivity, examine configuration, and test resolution. Remember that ExternalDNS automates Route 53 record management based on Kubernetes annotations. This is a common exam topic. Understand how network policies can affect DNS traffic and ensure proper ingress and egress rules for DNS queries. Practice the commands shown in this presentation. Hands-on experience with kubectl and Amazon Web Services CLI is essential for the exam. Congratulations! You now have a comprehensive understanding of DNS in AWS EKS environments. To continue your preparation for the AWS Network Specialty Certification, practice setting up EKS clusters using native AWS CLI commands and experimenting with different DNS configurations. Create test scenarios where you troubleshoot DNS issues, configure external DNS, and integrate with Route 53 resolver. The AWS documentation for EKS, CoreDNS, and Route 53 contains additional technical details that complement this presentation. Consider exploring advanced topics like DNS over HTTPS, custom DNS policies, and multi-cluster DNS federation as you become more comfortable with the basics. Good luck with your certification exam. The knowledge you have gained here will serve you well in both the exam and real-world EKS implementations.